Ocean Structures and Materials under the braces of NPTEL IIT Madras. In this specific lecture, we will talk about introduction to design of ocean structures, some of the important features and some of the methods and principles which are generally employed for designing offshore structures. Kindly note that this course does not address the detailed design procedures of offshore structures. We are only going to talk about introduction to design of offshore structures. If you look at some of the brief summary of few important factors which influence the design of offshore structures, they can be sequentially and preferentially in order or given below. The design methodology essentially differs with different types of offshore structures. The vertical deformation will be lesser in the case of fixed structures like jacket platforms, gravity based structures, etc. Compliant structures on the other hand are more flexible as they are displaced more under wave action. Floating structures are generally influenced by disturbing factors like waves, wind, etc., while restoring force is by gravity as variable buoyancy. The primary concept which comes into play when we talk about design of offshore structure is one of the important environmental load, which is the wave load. For estimating the wave forces on members of offshore structures, we first would like to know what is the design wave height, which I will consider in my design calculations. Offshore structural members are generally designed for significant wave height referred as HS in the literature. Significant wave height is defined as a representative value of the wave height for many purposes. It is defined as the average of the highest of 1/3 of the wave record given in a wave record. So, if you have a wave record which gives you the wave heights, arrange them in descending order, pick up the 1/3 of the highest of this, take an average of that, you call that value as significant wave height, which is defined as HS in the literature. So, HS is also defined as H suffix 1/3. It is because of the reason that HS is average of highest 1/3 of the waves in a given record. Therefore, H 1/3 is an alternative symbol which is used for HS. This is given by a simple equation of what you have here. In the absence of this, we can also find, if you have the wave spectrum or spectrum of the wave energy, we can also find significant wave height from the spectrum of wave energy using this equation, where MO is the first order moment of the spectrum. Also, if you have visual observation records of wave height measured in feet, then approximately from visual observations also marine experts calculate significant wave height using this expression, where HV in this expression is nothing but the wave height made by visual observation, and that value is given generally in feet. Therefore, the conversion of feet into meters will be taken care of by this multiplier and this constant. Therefore, if you are able to visually observe the wave heights in feet, then simply use this expression to find the significant wave height in meters. Now, once the significant wave height is known, one can estimate the maximum wave height by the given equation as you see in the slide now. It is obvious to note that the duration of the maximum wave height in a specific wave record is only for a very short period of time. Therefore, in the design it is desirable practice to account for the design wave height, which is given as follows. One may ask a question, why I cannot take the maximum wave height? It is very interesting to know, ladies and gentlemen, the maximum wave height generally prevails only for a very short period of time. Since it is only for short period of time, it is not advisable and it is not a preferential design practice to compute the calculations based on the maximum wave height, but people use the following equations for finding out the desirable wave height can be used in design calculations. For example, if you have a short term record, then extrapolate the waves for 100 years. For example, you do not have 100 years record, you have a very short term record, you can extrapolate that record using statistical principles for 100 years, then determine h 1/3 and then find h max based on this as given by this equation, which can be multiplied by a specific factor as advised in the literature. After understanding one of the important source of lateral load coming on the offshore structures, which is waves, structural form of members also play a very important role in preliminary design of offshore structures. Generally, the geometric layout of structural members is arrived on the basis of a preliminary analysis and design report, which we call as front end engineering design report, which is briefly said as FEED report. It is always customary to calculate or to carry out a design detailed feasibility study on the existing structure of a similar type. For example, we want to design a compliant offshore structure, it is always advisable that you conduct a detailed feasibility study on the existing compliant structure of a similar type to fix or to arrive at the basic structural form which will be appropriate for the selected site conditions. We have seen, ladies and gentlemen, in the lectures in the first module that the structural forms vary depending upon their site installation conditions. In case of structural geometry of offshore structures, form is essentially derived and designed based on the functional requirements, operational conveniences, construction difficulties like towing, method of launching, etc. So, the geometric form of an offshore structure is not only guided and designed or governed by the water depth, it is governed by many factors which are essentially functionally dominated factors and operational conveniences. People also look at what are the conveniences in terms of construction difficulties and installation problems. That is why we call this as a function based form, which is unusual in the case of other land based structures. Then one can think about how do I orient my offshore platforms, because wave directions can come in any angle of attack as far as the offshore structure is concerned. So, therefore, orientation layout of an offshore platform also plays one of a deciding role in preliminary design of offshore structures. Orientation is an important aspect in design of offshore structures. Preferred orientation is that members are generally oriented to have less projected area to the encountered wave direction. That is a general key rule. You should orient the structure in such a way that the members should have lesser projected area for the predominant wave direction which is attacking the structure. This therefore induces lesser responses on the members. Predominant wave direction for the chosen site is available generally to the designer. It is based on which the platform orientation is finally decided. If you ask me a question, what are those important list of data that are required to prepare or to start with the design of offshore structures? Interestingly, there are many data which are important, which you must have in hand before you start designing offshore structures. The first and foremost is that the land topographical survey of sufficient area covering the chosen site for the platform installation should be available to the designer, followed by which hydrographical survey details of the proposed location. Hydrographic charts are generally used for this purpose, and this detail should be available with the designer. This can give me information regarding silting at the site. Then windrows diagram can show me information on wind velocities, wind duration, predominant wind direction for round the year, which can be used in my design. Cyclonic tracking data should also be important, because this shows detail of the past cyclonic storm such that the wind velocities, direction, peak velocity period, etc. can be included in your design calculations. Oceanographic data generally has the following contents. General tide data includes the lowest water level recorded, the mean low water spring, the mean low water neaps, the mean sea level value, the mean high water neaps and the mean high water spring, the highest water level recorded at a specific site, followed by which the tide table will also show if there is any abnormal variation in tide levels in the specific site. Wave data is an important category of data which is necessary for designing offshore structures on a specific site. Wave data includes the maximum wave height and the conditions prevailing at that time, significant wave height, period and wavelength which can be considered for the design calculations, wave roses of observed waves, storm surge details, long period wave data if it is available in a specific site, followed by which information regarding current is also equally important, because current data includes the following like seabed characteristics showing seabed levels, composition, bed slopes, etc. You should also have a data of temperature variation round the clock round the year. A rainfall average for the past 10-year record is mandatory for planning and designing offshore structure in any chosen site specific location. Of course, you should have a record based on humidity round the year, followed by which most importantly, ladies and gentlemen, because of the tectonic movement happening in the recent past, seismicity level and values of acceleration are also becoming important piece of information which is required for design of offshore structures. Structural data of existing similar structures in the nearby vicinity is preferably important, because they can be also parallelly used as a basic dimension for computing the member sizes for the offshore structures. To fix up the foundation type, the foundation depth, etc., one should require detailed soil investigation report of a specific site. Once I have defined the form for a specific offshore structure, once I have chosen the site, once I have the oceanographic, hydrographic data specific site, then I am interested to find out what are the wave forces coming on the members in the offshore structure designed and located at this specific site. The wave forces and current forces generally are handled in the design by two methods, namely design wave method and spectral method. In the design wave method, the design wave height H max is directly obtained from the time history of the existing wave record. Ladies and gentlemen, in the previous slides we showed you different expressions for working out H max or design wave height from a given wave record. Any one of them can be used to fix the design wave height for the current problem. Of course, alternatively in the spectral method, the time history of the wave record is converted into a spectrum. You can always do conversion of time history into a frequency domain using Fourier transforms relationship. Subsequently, every structural member is then designed for each frequency content input of the spectrum. Use of Morrison equation to estimate wave forces on members have of course their own limitations. The basic assumption in using Morrison equation is that the flow is assumed to be not distributed by the presence of the structure. This is true and applicable only when D by L ratio is far less than 0.2, where D stands for the diameter of the member and L stands for the wavelength. Current velocity present in the sea surface also dominates and influences the design parameters. As waves and current propagate in the same direction, wavelengths actually get stretched. There is a significant change in the wavelength when current is also acting along with the wave in the same direction. The corresponding wave period of the stretched wave is generally addressed as apparent wave period, which is indicated as T suffix apparent in the literature. This is explained and examined as Doppler's effect in the literature. So, Doppler's effect is nothing but accounting for stretching of the wave period because of influence of current on the wind or on the wave in the direction of propagation. As a result, the wave height increases and vice versa, that subsequently it modifies the wave period which is used in the design calculations. American Petroleum Institute API code gives a modified wave period which can counteract this variation due to the presence of current on wave stretching. In the API procedure, wave kinematics is computed in a single coordinate system moving at a steady current speed using this apparent wave period. This accounts for Doppler's shift in the wave frequency. So, API procedure indirectly recommends a shift in the wave frequency because of stretching of waves whose wavelength is increased in the presence of current. Ladies and gentlemen, this figure shows what is the variation which can be having or which occurs from the Doppler shift due to steady current, which is taken from API RP2A as a courtesy. So, once the wave kinematics is determined, combined wave current velocity are then used in the traditional modification equation to estimate the wave loading. In the absence of this detailed effect of Doppler's effect on stretching of waves because of presence of current, the Doppler's effect is computed on the basis of ambient current velocity in the direction of waves, as you saw in the last slide. For the known variation of current velocity along the depth, apparent wave period can be computed using analytical relationships as given by Chakravarti in 1984. So, the apparent wave period can also be computed based on this expression, where L by T is given by L by T apparent plus U apparent, where U apparent is given by this equation where the current velocity is included in the discussion somewhere here in U apparent. In the whole discussion, U apparent is the weighted mean velocity that is obtained by integrating the current velocity over the entire water depth, because the integration in this equation, if you see, is for the domain of entire water depth, where small d stands for water depth. The other alternate parameter, and which is a very parallel and influential parameter that significantly contributes to the preliminary design of offshore structures, is marine growth. When the members are installed in sea, because of its presence of external agencies in the seawater as well as presence of marine aquaculture in the vicinity of the members, there is always expected that the marine growth may get formed and deposited all along the circumference of the cylindrical members. Marine growth is seen as an evidence from the studies that the extent of this growth on the surface of the members is usually about 50 millimeter, can be as thick as 150 millimeter, which gets deposited along the periphery of the member. The marine growth increases obviously with the increase in diameter of the member, because it enables more contact for them, and when the marine growth gets deposited along the circumference of the member, it starts attracting more forces. All structural members therefore should be designed for the increase in cross sectional area which is effectively occurred because of formation of marine growth along the surface or along the periphery of the member. So, one should account for what is called as marine growth thickness in the design of offshore structural members. On the addition, members should be also classified either as smooth or rough, because the drag and inertia coefficients for the surface roughness of the member are different, which are generally advised by different international codes. So, the smooth or roughness, depending on the amount of marine growth expected on these members, becomes a very vital parameter to fix up the Morrison coefficients, that is drag coefficient and inertia coefficient, which are otherwise used in the force estimates of the member. However, it is a conventional practice to increase the member forces by about 20%, which can account for this additional forces attracted by the members because of marine growth. Ladies and gentlemen, it is very interesting for you to know the density of marine growth is about 1300 kg per cubic meter. So, this is significant when the volume or when the deposition thickness of the marine growth is phenomenally high around the surface of the member, which is generally high near the seabed. When you got series of members which are arranged in a row or group of members which are placed in a location, then they also call or they cause basically what is called a blockage factor. Now, what is a blockage factor? For a typical design of offshore structural members, drag and inertia coefficients are generally recommended from the American Petroleum Institute codal provisions. For unshielded, for example, there is a circular cylinder which has got no members in the near vicinity, we call this as unshielded circular member, and if the member is smooth, it means the member does not have any marine growth sticking onto the surface of the member, we take the drag coefficient as 1.05 and inertia coefficient as 1.6 as recommended by APA. However, if the surface of the cylinder becomes rough because of deposit of marine growth along the periphery of the member, it results in some imperfections on the surface of the member, and therefore, CD remains same, but CM is reduced drastically from 1.6 to 1.2. Alternatively, offshore platforms also cause blockage to current flow in water waves, because they obstruct the flow of free surface of water from flowing from one direction to the other. This creates an additional effect on the members which is otherwise called as blockage factor. In such cases, the current speed in the vicinity of the member is reduced significantly in comparison to the free stream values. This is what we term as current blockage factor. This should be accounted in the design. API recommends current blockage factor variation from 0.7 to 0.9. Having understood how to calculate the water particle kinematics using Airy's wave theory, having understood how to calculate the forces using Morrison equation, having learned how to modify the inertia and drag coefficients which are used in Morrison equation because of presence of current which causes blockage factor as well as stretching of wavelength which is called Doppler's effect, then one is interested to know what are the different methods of force estimates which can be applied to compute forces on the members of offshore structures. The global structural force on the members can be calculated by two different methods, namely maximum base shear method and maximum overturning moment method. In the maximum base shear method, the vertical cylindrical member is divided into equal number of parts along its length. The lateral forces which are caused by the waves are computed at the centroid of each divided length of the member. Then we do a vectorial summation of all these forces which will give me what is called maximum base shear, for which the member shall be designed. So, this method, since it accounts for the summation of lateral forces which is acting at centroid of every segment of the member along the length, which becomes a base summation of all the forces at the bottom, we call this method as base shear force method. Maximum overturning method is also used when the lateral forces are computed at the centroid of each segment of the member causes moment about the bottom of the member. In addition, to estimate the total lateral force, which is the vector sum of the lateral forces acting on each segmental length, overturning moment caused by these forces at the base of the member is also parallelly computed. Ladies and gentlemen, let us look at two equations, which is the force total and the moment total. The force total, as you see, if you divide the members into n number of parts equal or unequal varying from the bottom, whereas y becomes 0 at the seabed and y keeps on increasing as you move towards the mean sea level. You divide the member into n number of segments, each segment try to fix the centroid of the segment, because you know the geometric dimensions of this segment, you can always find the geometric center of this segment, measure the distance of that from the fixed end. I call that as yi. I is the ith member which can be computed. Now, once I get the forces in each segment, sum all of them, as you see in this equation, find the total force acting at the bottom, which we call as base shear method. Also, at every point, as you see here, you know the forces because you know the segment in length and the force acting on the segment. Sum up all of them, find the forces, find the moment of each one of them, about the bottom find the moment, because moment is the force into the distance of that particular centroid from the seabed, which is yi, which is shown here as y1, y2, yn, etc. So, you will also find that the total force will act at a specific location from the seabed, and the total moment of course in this example will be at the bottom, because the bottom is fixed end for this member. After knowing this, the global structural forces are then calculated by a vectorial summation of the following. 1. Compute the local drag and inertia force caused by the waves and current in each segment. Compute the wind forces on exposed portion of the structure. While calculating the forces due to waves, wave crest should be positioned relative to the structure, so that the total base shear and overturning moment becomes the maximum. Remember this, we are not trying to work out the forces at instantaneous position of the structure. We are hypothetically saying that the wave crest should be positioned relative to the structure in such a manner that the total base shear and the total base moment produced by these forces should become obviously the maximum, because then this design will be called as highly conservative design. So, the maximum local lift per unit length of the member is given by this equation, where L max stands for maximum lift force and CL max stands for the lift coefficient. Generally, which is taken as 0.7 of the drag coefficient. Of course, in this equation omega is the density of sea water, d is the effective diameter of the member, and u max is the component of the velocity vector normal to the axis of the member. D is an effective diameter which includes the effect of deposit of marine growth along the member. Therefore, your member diameter d is not as same as the member diameter which you have used while installation and design. In due course of time, this d can be changed, because this d is an effective diameter of the member. Now, for the natural frequency of the member closer to the lift force frequency, a very large amplitude of the vortex induced vibration will occur, which causes the member to fail. So, you will get an idea at what frequency range you get critical loads acting on the offshore member. If you look at horizontal members in splash zone, they experience very high slam forces. Slam forces are nearly vertical forces that are caused by local water body or water rising surface and slapping against underside of the member as the wave passes. The slam force per unit length, indicated as F suffix s, is given by the following equation now you see on your screen. These forces are nearly vertical and they do not account for base shear and overturning moment. So, very importantly, slam force are almost vertical. Having said what will we compute or what methods are generally there for estimating forces on members of offshore structures, we will now talk about the design methods. Design of offshore structure includes 3 methods in practice, namely working stress design method called as WSD, limit state method or load and resistance factor design, which is called as LRFD, and of course, the third method, which is innovative and practiced in modern design offices, is the plastic design method. In working stress design method, the allowable stresses are generally recommended for the members subjected to different combination of forces acting on the member, namely tension, compression, bending, shear and fatigue. According to American Petroleum Institute codal provisions, the allowable stresses for different structural actions are fraction of the yield stress of the material. For example, if you take Fy as the yield strength of the material, then obviously for different structural actions the acceptable allowable stress is nothing but a fraction of the yield stress. It is not same as the yield stress. Linear elastic analysis are also generally performed, and the maximum stresses thus obtained on the members shall not exceed the allowable stresses recommended by the code. For example, API. Let us quickly see what are the factors which are considered for different load combinations or independent actions on the members. So, if you look at this table, for axial tension, the maximum stress value permitted in the code is 0.6, whereas for axial compression it should be less than 0.6 Fy, for bending it should be less than 0.7 Fy, for shear it should be equal to or less than 0.4, whereas torsional shear they should be less than or equal to 0.4 Fy again. Once you have estimated the service loads on the members, it may not guarantee any accuracy because these loads keep on varying depending upon the sea state and the environmental critics happening at that sea state. The method of design is actually case specific. One should know how I am doing the method of design, because design is nothing but checking the safe stress limits with arbitrary recommended allowable stresses which has no justification, because I have got to compare the generated stresses with that of the recommended allowable stresses which are given in the code. And what are these stresses? They are seen in the table given below. If a subjecting a member to pure axial tension only, then the permissible stress value is only 0.6 of Fy, and so on so forth. Talking about axial compression, talking about torsional shear, then the combination or the factors or the permissible stress values which are acceptable in the design vary as per the table seen just now. So, the method of design is acceptable only for preliminary design stages. It cannot be carried forward for instrumental or for implemental stages, because they are generally used only to arrive at the sizing of the member. Allowable stresses recommended by API for different structural actions are given in the table below. Once I get the allowable stress value, can always design the member, or I can get the permissible value, get the dimensions of the member, which is otherwise called as design of the structural members of offshore structures. Now, alternatively, in the recent past, researchers have started practicing what is called plastic design in offshore structures. Let us see what is a plastic design very quickly. In plastic design, structural behavior of the material is considered up to ultimate load stage, whereas in LRFD it was not true. This method of design is advantageous because it is a very good alternative for the design based procedures as suggested by working stress design, because working stress design uses elastic analysis, whereas plastic design uses plastic analysis. This method of design is very highly recommended for structures with high degree of indeterminacy. The moment I say indeterminacy, it includes both kinematic and static indeterminacy. So, if you have got an offshore platform with a very high degree of indeterminacy, both static and kinematic indeterminacy, then one can go for plastic design as recommended for this type of structures. Offshore structures therefore, being an indeterminate of very high order, are potential candidates for plastic design. In this method of design, the strength of material is not stretched beyond the yield strength of the material. There is always a wrong convention with designers saying that in plastic design the stress value will exceed Fy. The stress value never exceeds Fy. The method of design is rapid and simple. Member sizings can be always lesser than that derived from the conventional elastic analysis like working stress design. So, plastic design leaves an economical sizing of the member the yield stress are never increased or never touched upon to be its optimum value in the design, etc. Plastic analysis and design therefore essentially deals with failure phenomena of members. The failure phenomena can be local because the member can fail, it can be global because the structure whole can fail. It is important to note that the plastic analysis and design assumes as the structure collapses will be only due to plastic deformation. No pre-included collapse mechanisms are there considered in the plastic analysis. Plastic analysis and design purely assumes that the structure collapse only due to plastic deformation. Other factors can influence premature failure, but generally these factors which are contributing to premature failure are generally excluded from the consideration in plastic analysis. I can give an example how do you say premature failure can occur in an offshore member. Now let us take a cylindrical member subject to axial compression. When the cylindrical member is very large in length compared to the least little dimension of the member, before the member fails in axial compression, there is a possibility that the member may buckle. Therefore, the buckling effect on the member can cause a premature failure. Of course, in plastic design these kinds of premature failure are not accommodated. In plastic design, service loads which are acting on the member are factored, basically they are multiplied by a load factor which is assumed to fail under these loads when plastic hinges are formed at critical sections. Ladies and gentlemen, in a plastic analysis you must understand what do we talk about critical sections. Critical sections are not the locations where the bending moments are maximum, it are the locations where a combination of good amount of plastic hinges can be formed because of the geometric variation, because of the load concentration, because of the variation in moment of inertia, or because of the sway mechanism imposed on the structural configuration of the platform. In plastic design, service loads are generally factored by a load factor and they act at very specific critical sections. Few limitations in plastic design are very important to be considered. One, it preludes other stability fatigue issues that influences a premature failure. Uncertainty in material strength is completely neglected in plastic design. There is an arbitrary choice of the total load factor which can be a subject of question. So, the load factor which is an arbitrary value selected which is a subject of interest is defined as the ratio of collapse load to the working load, which is given by a simple expression as you see on the screen now. As the service loads are factored in the plastic analysis and the allowable strength is close to the yield strength of the material, one may think about factor of safety involved in plastic analysis and design. Ladies and gentlemen, very importantly, please understand that the service loads are increased by a factor, whereas the yield strength of the material or the allowable strength of the material is closer to the yield strength of the material. Now one may wonder, is there really any factor of safety involved in plastic design methodology? On the contrary, in the working stress design, factor of safety is explicitly seen because factor of safety is nothing but the allowable stress fraction of yield stress. So only a fraction of yield stress being recommended as an allowable stress. Therefore, you explicitly see the factor of safety in working stress design. The load factor Q, which accounts for the margin of safety in plastic design, is therefore explained below. Let us say the M is proportional to W, or M can be a multiplier constant with the working load W, where M is the applied moment at the cross section in elastic analysis and W is a load on the member and K of course is what we call as load factor. Similarly, in plastic analysis, the plastic moment of resistance MP is given by a simple equation as you see here. When you follow the equation, you will notice that Q, which is nothing but the ratio of the plastic moment to working moment, is a product of shape factor to factor of safety, because the ratio of plastic moment of modulus the elastic moment of section modulus is nothing but the shape factor, and this is what we generally use as a factor of safety even in our working stress design. Therefore, in plastic analysis and design methodology there exists very interestingly a factor of safety which is again comparable to the factor of safety available in working stress design methodologies. Thus, the load factor is nothing but a product of the shape factor and factor of safety which is similar to that used in elastic analysis. Therefore, a load factor Q which accounts for margin of safety in the plastic design can be considered as a margin of safety which you see here in other design factors. Now, let us consider an example to understand the magnitude of factor of safety in plastic design. Let us say for example, Fy be the yield strength of the material. In an axial tension, the permissible strength is generally taken as 0.6 of the yield strength. Therefore, one can see that the factor of safety is 1.66, which is nothing but 1 over 0.6. However, interestingly in plastic design, the load factor Q accounts for a factor of safety as I discussed in the previous slide. As given in the equation earlier, Q becomes a product of shape factor and factor of safety. Therefore, for a given cross section with shape factor of 1.2, you may wonder what is that cross section which has got a factor of 1.12. For example, this can be a rolled steel I section. So, let us say the shape factor for a rolled steel I section which is commonly used in offshore structures has a shape factor of 1.12. Therefore, the load factor which is 1.12 multiplied by 1.1666 which gives me 1.85, which is comparably good with that of the working stress design. Hence, the margin of safety in plastic design is no way lesser than that is considered in working stress design. Alternatively, people also follow a other design methodology which is called as limit state design methodology. In limit state design methodology, the condition is that is reached at which the structure or a part of the structure ceases to perform its intended function. That is why we say the function has reached its limit state. LRFD method is basically an extended technique of limit state design where load resistance factor design method which is expanding LRFD. LRFD is based on limit state philosophy. Service loads are generally multiplied by a load factor R and the linear elastic analysis is performed to compute the values. So, the material strength is of course reduced by multiplying a resistance factor. Conceptually, it is given by the following equation as you see on the slide now. Load and resistance factors are therefore developed from probabilistic distribution. This method of course ensures lesser probability of failure as compared to the load factor which accounts for variability in loads considered in the analysis, while the resistance factor accounts for material property variability and consequence of failure, etc. So, there are various parameters considered inherently in the design methodology in limit state technique as you see on the slide now. Therefore, you can always summarize this resistance factors which are used for LRFD as given by international codes for different kinds of load types like axial tension, axial compression, bending, shear, buckling connections, etc. You have got different resistance factors suggested by international codes. So, the summary of the table shows you what are those resistance factors which are depending on what kind of load is acting on the member. Now, let us quickly summarize what are the steps involved in structural design of offshore structures. Following steps are identified as necessary to carry out structural design of offshore structures. In step number 1, you estimate the wave height, wave period, current distribution along the water depth. In step number 2, you establish appropriate wave theory that is suitable for the chosen site location of the platform. In step number 3, you will estimate the water particle kinematics, that is water particle velocity and acceleration both in horizontal and vertical directions. In step number 4, choose appropriate values of the drag and inertia coefficient. Ladies and gentlemen, in this lecture we understood how to select CD and CM values based on Doppler's effect and correction effects as given by API. In step number 5, you establish marine growth thickness and account for this thickness in the design. In step number 6, you check the wave kinematics factor with respect to the current, which we call as Doppler's effect. In step number 7, determine the current blockage factor and make suitable modifications in your force estimates. In step number 8, check the appropriate modifications deemed necessary for the Morrison equation and ultimately design the members. So, ladies and gentlemen, in this lecture we have learned the preliminary methods and steps involved in design of offshore structures. Of course, this course does not address the design methodology in detail. We have seen in this module, in this lecture, how to design preliminarily the offshore structural member design. In the next lecture, we talk about the construction methodologies and installation techniques for offshore structures. Thank you.